Today on AI Paperslop, we are unpacking world models meet language models on the complementarity of concrete and abstract reasoning by Yucheng Zhu and colleagues.
Right.
If you are an ML engineer or a researcher building agentic pipelines, you really need to hear this one. Multimodal large language models are phenomenal at abstract reasoning. Rules, goals, logic.
Yeah, the high-level stuff.
Exactly. And generative world models are phenomenal at concrete reasoning, like visually simulating physical futures. But, and this is the kicker, simply slapping a world model onto an MLLM as an API tool completely breaks down.
That's a total mess.
Yeah, the paper identifies two massive failure modes right out of the gate. First is simulation inertia, where the MLLM just stubbornly ignores the world model.
It's like it doesn't even exist.
Right. And second is the forced simulation paradox, where if you force the MLLM to use the world model, it actually degrades accuracy because it just blindly trusts hallucinated physics.
Which is such a weird behavior.
It is. So the breakthrough solution they propose is PFOPSD, or Privileged Future On Policy Self-Distillation.
Quite a mouthful.
A bit, yeah. But basically, it's a framework that trains the MLLM to act as a highly sophisticated controller. It knows exactly when to invoke a simulation, how to prompt it, how to verify it, and how much to rely on it. And it learns this using ground truth future videos purely as privileged training signals.
Yeah.
So let's look at why the baseline approaches are failing so spectacularly.
Well, the pathology of that failure reveals a lot about how these architectures currently perceive the world, how they reason. To understand why naive integration fails, we have to look at the exact mechanics of this complementarity between abstract and concrete reasoning.
Okay, unpack that a bit.
Sure. So MLLMs organize goals and physical laws in language. If you prompt an MLLM about an apple dropping from a tree, it accesses an abstract prior. It can, recite Newtonian mechanics perfectly.
Right, it knows the math.
Exactly. But a world model makes that future visually explicit.
Mm-hmm.
It actually renders the apple detaching, falling through the air, making contact, and rolling realistically based on the terrain geometry.
So it's the physics engine.
Yeah, it's the physics engine. Naturally, the assumption in the field has been that combining them gives you the ultimate predictive agent.
Yeah.
The abstract engine handles the logic, and the concrete engine handles the rendering.
Which makes sense on paper. But the authors tested that assumption. They ran a preliminary diagnostic using a Gemini 3 Flash and Qwen 3.59b, and they paired them with the Helios world model.
And it was a disaster.
Totally. The moment they gave these state-of-the-art models this powerful new rendering tool, the models effectively refused to touch it.
The numbers really highlight just how stubborn these abstract models are. Under an optional tool use setting, the models exhibited what the authors term simulation inertia.
Which means what, exactly?
We are talking about a 96 to 98% no-call rate.
Wow.
Yeah. Even when the prompt explicitly encouraged them to use simulation for complex spatial tasks where pure language models notoriously struggle, they just defaulted to their own abstract priors.
It's honestly like pairing a brilliant theoretical physicist with a lab technician. The theoretician has all the equations in their head, so they just arrogantly refuse to ask the lab tech to run an actual experiment.
That's a great way to put it.
They're entirely convinced they don't need the concrete empirical data, even when the math is just overwhelmingly complex.
And the problem intensifies when you try to engineer around that arrogance. The standard industry fix to tool use inertia is to, hard code the pipeline.
Right, you rewrite the system prompt.
Exactly. You force the generation loop to say you must run a simulation and incorporate the rollout into your context window every single time.
Right.
But when the researchers did this, it triggered the forced simulation paradox.
Where the overall accuracy actually dropped.
It fell noticeably. On their VRQABench dataset, accuracy dropped from 33.2% to 32.6% when simulation was forced.
Which is wild. Why does forcing more data make it dumber?
The mechanism behind this drop is crucial. Generated rollouts from world models are not precise deterministic oracles. They are noisy, stochastic reasoning traces.
Hallucinate.
Exactly. They might look visually plausible at a quick glance, but they frequently miss task-critical interactions, where the geometry just drifts over the course of the video.
So going back to the physicists and the lab tech, it's like forcing the arrogant theoretician to use the lab tech's data.
Yeah.
But because the lab tech's equipment is glitchy, the data is sometimes flawed. The theoretician, who never wanted the data in the first place, has zero framework for evaluating its quality.
Right, they just accept it.
They blindly paste the flawed experiment into their math, the delicate chain of thought is totally disrupted by stochastic noise, and they completely ruin the final paper.
That's exactly what's happening. The underlying bottleneck isn't a lack of access to predictive pixels. The bottleneck is control. Yes. The MLLM lacks an explicit decision-making framework to govern how it interacts with the tool. It needs a mechanism to arbitrate between its own abstract priors and the rollout-based evidence.
It has to know when to trust the lab tech and when the lab tech's equipment is malfunctioning.
Spot on.
Okay, so that structural necessity brings us to the formalization of what the authors call controlled concrete reasoning. Because if naive integration leads to either ignoring the tool or trusting it blindly, you have to build an architecture that forces the model to manage the tool methodically.
Right. And the way the paper formulates this interaction is highly systematic. They dictate that the MLLM cannot just passively receive a video feed. It must actively emit a concrete reasoning trajectory.
What's a trajectory?
Yeah. They define this as an action space with 5 distinct sequential control states.
Okay, let's walk through those. The first state is decimal-M, which is just the binary decision to simulate.
Yes. The model looks at the static input and decides if a visual rollout is actually required to answer the prompt.
And if it outputs yes, it moves to the second action, the simulation prompt. And this isn't just a generic run simulation command.
Far from it. The model actually has to write the conditioning prompt for the world model. It specifies the focus.
Oh, wow.
Yeah. For example, it might generate text commanding the world model to trace the trajectory of the red block at coordinates XY. It is actively setting the parameters for its own sub-agent to ensure the resulting video highlights the specific spatial interaction needed.
That's really clever. So once the world model generates that video, the MLLM executes the third action, Zyver, which is rollout verification.
Right.
The MLLM examines the generated video and classifies it into one of 3 buckets: accept, reject, or uncertain. This acts as the internal quality control.
And this verification step is tied directly to a built-in retry mechanism.
Like a loop.
Yeah. If the MLLM observes that the physics engine hallucinated, say, 2 solid objects just clipped right through each other, it rejects the rollout and triggers a prompt retry. It gets to refine its sense of instructions and try again, up to a hard cap of 3 simulation attempts, per example. So you avoid infinite generation loops.
Right. But I actually want to push back on the fourth action here. The fourth step is rollout reliance.
Okay.
This dictates how much weight to give the rollout before making the final answer prediction, which is y'all or ball. But wait, if the model verified the rollout in the previous step and explicitly decided to reject it because it was glitchy or hallucinatory, why does it need a reliance state at all? If the data is garbage, shouldn't the model just flush it from the context window entirely and move to the final answer?
It seems counterintuitive, I know, but retaining that reliance state is vital for complex spatial tasks.
Yeah.
Rejected rollouts are heavily discounted, absolutely. But a rollout isn't always binary garbage.
What do you mean?
Well, imagine a 30-frame video. The physics engine might break completely at frame 15, causing a rejection. However, in frames 1 through 14, the world model might have successfully isolated the target object from a highly cluttered background.
Oh, I see. Something the language model's static vision encoder really struggled to do.
Precisely. So the reliance state allows the MLLM to synthesize those useful early fragments while falling back on its own abstract reasoning for the actual collision prediction.
So it's salvaging partial spatial cues? It prevents the model from throwing out the baby with the bathwater?
Exactly. Balancing whatever empirical evidence is salvageable against its own internal logic.
That makes perfect sense. Okay, so we have this highly complex multi-step trajectory. The model decides when to call, writes a targeted prompt, evaluates the video for physical consistency, loops back to retry if necessary, and then mathematically weights the evidence to guess the final answer.
It's a lot.
It is. And if you are an ML engineer listening to this, the immediate question is, how on earth do you optimize a multi-step trajectory like that? Standard supervised fine-tuning, where you just show the model the final correct answer, isn't going to teach it all these intermediate arbitration skills.
No, standard FFT will completely fail here. SFT can teach syntax, but cannot teach judgment. That is the exact problem the authors solve with their 2-stage training pipeline, which culminates in privileged future on-policy self-distillation, or PFOPSD.
Here's where it gets really interesting. Let's break down that pipeline. Stage 1 is protocol SFT. This is purely formatting, right?
Yeah, they use trajectories generated by a highly capable agent, Gemini 3.1 Pro, to basically teach the student model how to emit the correct tokens for SM, Tia's drill on the right syntax.
Just getting the formatting down.
Exactly. But stage 2, the PFOPSD, is where the actual intelligence is injected.
Right.
The core of stage 2 relies on the concept of asymmetric information or privileged context. Think about standard reinforcement learning. Standard GRPOs like grading a student solely on their final exam score.
If they get the right answer, they get a reward.
Yeah, regardless of how messy their math was. But PFOPSD is like a teacher standing directly over the student's shoulder, grading their scratchpad math at every single step of the equation.
Because during training, there is a teacher evaluator in this architecture. It's Quen 3.627b, and the teacher gets to see the ground truth future video, denoted as $V, and the final ground truth answer, $A.
Right, the teacher has the answer key and the perfect physics render.
Meanwhile, the student model generates its on-policy trajectory based only on the first frame of the video. It is totally blind to the future.
Completely blind. It decides whether to simulate. It receives a noisy rollout from its world model. It attempts to verify that rollout, and it makes a guess. The teacher model then scores that entire trajectory.
And crucially, the teacher calculates advantage-weighted targets for the intermediate decisions. This is essentially an on-policy advantage formulation, kind of like PPO or GRPO, but explicitly assigning credit to the intermediate concrete reasoning decisions, not just the final answer.
Let's explain the math behind that conceptually. The teacher looks at the noisy rollout the student generated. If the student put a yes for verification, meaning it accepted the video, but the teacher compares that rollout to the true future video and sees a massive visual delta.
A huge difference.
Yeah, the algorithm applies a heavy negative advantage score, specifically to the tokens where the student chose accept.
So it forces the student's internal weights to adjust towards skepticism.
Exactly. The teacher heavily penalizes false accepts, where the student trusts a bad video. It equally penalizes false rejects, where the student discards a perfectly good simulation.
And it penalizes unnecessary calls too, right?
Yes, it applies a consistent penalty for unnecessary calls, aggressively curing the simulation inertia from the baseline. The student is constantly recalibrating its confidence based on the teacher's privileged feedback.
And the beauty of this is deployment. At test time, the teacher is completely removed. The deployed student has zero access to the true future, but it has completely internalized the teacher's judgment.
It operates as its own highly calibrated, autonomous controller.
But, if you've built this intricate skeptical controller, you have a massive evaluation problem. You cannot run this against standard visual QA datasets.
Oh, definitely not. Standard datasets test for static object recognition or basic spatial relations. They do not test for temporal look-ahead or physical prediction from a static observation.
Right.
If you want to prove your controller actually understands future states, you have to build entirely new arenas from scratch. So the authors developed 2 human-verified benchmarks.
The first is VRQABench. This benchmark consists of 4,636 items focused heavily on controllable spatial look-ahead. We are talking about grid-based environments, mazes, irregular mazes, and Sokoban puzzles.
The classic block-pushing game.
Yeah, and what makes VRQABench mechanically robust is the ground truth. They used programmatic solvers to guarantee the optimal path.
So there's no ambiguity or human labeling error.
Exactly. The model looks at a static image of a complex maze and has to predict exact programmatic outcomes, like how many specific left turns exist in the shortest path to the goal.
But the real world isn't a sterile grid, which requires the second benchmark, OpenWorld QA. This dataset contains 4,404 items and forces the model to predict real-world physical outcomes. It utilizes natural videos, but the testing model only ever sees a static anchor frame.
Which is just a single image captured milliseconds before the main physical event occurs.
Picture a static frame of a heavy glass tipping perilously over the edge of a table right before gravity takes over. The model has to predict the exact physical consequence.
And creating this dataset required a highly complex 5-stage agentic pipeline. Scene analyst, question designer, distractor forge, small model probe, and reviewer.
The pipeline was intense.
I really want to highlight the distractor forge step because it solves a notorious problem in benchmark design generating physically plausible wrong answers. If the question asks where a bouncing ball will land, a terrible distractor is the ball turns into a bird.
Right. The language model will just use common sense to eliminate that without doing any physical reasoning at all.
Exactly. Distractor forge uses specialized prompt to generate answers like the ball bounces at a 45-degree angle instead of a 30-degree angle. Beating that requires genuine spatial prediction.
And to guarantee that the distractors were bulletproof, they implemented the small model probe.
This part is so cool. How do they ensure the MLLMs weren't just guessing based on obvious visual cues?
Well, they took every candidate question and fed it to a tiny GPT 5.4 nanomodel. If that lightweight model could guess the correct answer twice in a row, the authors instantly flagged the question as too easy.
Wow.
It meant the answer could be deduced from obvious visual biases in the anchor frame without needing actual forward simulation. They deleted those questions entirely.
It's an incredibly rigorous methodology. So we have the controller mechanism trained via PF-OPSD. We have the dual evaluation arenas of VRQABench and OpenWorld QA. When you put this learned controller to the test, what do the metrics actually look like?
The top-line results definitively prove the architecture. PF-OPSD achieves 72.4% accuracy on VRQABench. That is a 10.6% absolute improvement over the standard SFT baseline.
That's a massive jump.
It is. And on the real-world physics of OpenWorld QA, it hits 70.5%, which is a 10.9% improvement over SFT.
It also significantly outperforms the SFT plus standard GRPO baseline.
Yes.
That delta proves that just applying reinforcement learning to the final answer isn't enough. You absolutely need that intermediate trajectory credit assignment to build a functioning orchestrator.
The performance jump is impressive, but the rollout diagnostics are what truly validate the controller's behavior. Remember that in the baseline, the models stubbornly refused to call the tool.
Right, the simulation inertia.
Exactly. The PFOPSD model learned an optimal selective balance. It only invokes the world model on 42.5% of the examples, averaging 0.45 calls per question.
So it evaluates the static frame and makes a calculated choice. If the question is simple enough for abstract logic, it skips the API call entirely, saving compute.
Yes.
If the spatial dynamics are complex, it calls the world model.
And its internal quality control is incredibly sharp. Under isolated testing, the PFOPSD controller accepted high-quality rollouts 92.5% of the time. But when the researchers deliberately sabotaged the tool by feeding the controller corrupted rollouts,
It caught them.
its acceptance rate plummeted to just 5.2%. It successfully identified the hallucinated physics and discarded the bad evidence.
That's amazing. There's a specific stress test in the paper that I think is the ultimate proof of this entire architectural philosophy. They performed a cross-world model diagnostic.
Oh, this is fascinating.
During the PF-OPSD training, the controller learned its arbitration skills working exclusively with the Helios world model. At test time, the authors secretly swapped out Helios and replaced it with WAN 2.2.
Which is a strictly superior, highly advanced generative world model.
Right, so they set up a direct comparison. First, they ran an unconditional always simulate policy using the vastly superior WAN 2.2 model. Second, they ran the selectively controlled PF-OPSD policy, still relying on the demonstrably weaker Helios model.
And the results of that swap are profound. The selectively controlled PFOPSD model, using the weaker Helios tool, achieved higher accuracy than the always simulate model using the superior WAN 2.2 tool.
That is just, if you are managing an AI tech stack, this is the ultimate validation. This proves that a smart manager, the PFOPSD controller, working with a mediocre intern, the Helios model, will actually outperform a terrible manager working with a genius intern like WAN 2.2.
What's fascinating here is that it proves that the integration mechanism is vastly more important than the raw generative power of the tool itself.
Yeah.
Improving the pixel-perfect quality of your world model is a worthy pursuit. But if the orchestrating language model lacks the framework to scrutinize and manage that generation, you are leaving massive performance on the table.
And introducing severe hallucination risks into your pipeline.
Exactly.
So what does this all mean? Zooming out, adding a world model, or frankly, any complex generative tool to an LLM architecture is not a silver bullet. You cannot just bolt it on via an API and expect magic. The integration bottleneck is control arbitration between abstract priors and rollout-based evidence. So, if you are designing your own agentic pipelines today, your priority has to be training your orchestrator to be a skeptic. But the methodology used here to train that skeptic opens up an entirely new set of problems.
It raises a highly provocative question regarding the scalability of autonomous agents. To train this meticulous skeptical controller, the architecture absolutely required privileged teacher data.
It needed ground truth future videos that the student model did not have access to.
Right. If the future of AI relies on MLLMs systematically distrusting and meticulously verifying their own internal tools based on asymmetric teacher data, do these agents now require constant privileged calibration environments for every single new tool they adopt?
And what happens when those tools become too complex?
Exactly. What happens when the operating environment is so novel or the tool is so advanced that even the privileged teacher cannot verify the ground truth? Does our ability to scale agentic tool use hit a hard ceiling defined entirely by our ability to curate privilege calibration data?
That is a staggering implication to end on. If the smart manager requires a CEO with perfect foresight to teach it how to manage the intern, the whole system breaks down the moment nobody in the room knows the right answer. To everyone listening, if you are wrestling with tool integration and hallucination loops in your models, you really need to read World Models, Meet Language Models by Yu-Cheng Zhu and team. Stop letting your theoreticians blindly trust glitchy lab techs. Until next time, keep diving deep into the slop.